So here we go, Chapter 5 on gases. First thing we're going to do is check out the difference in um, solid, liquid, and the gas state. So you notice in the gas state, molecules are very far apart, moving very quickly, and there's a lot of space there that we can actually use up by compressing those molecules. In the liquid and the solid states, the particles are just about touching, so they're not compressible at all. There's a lot more motion in the gas state, and much less as you go to the liquid and the solid states. You notice in the solid state, the particles line up pretty evenly and regularly, yet in the liquid state, even though the volumes look pretty much the same, they're not lining up very well at all. Okay, next thing we have is just let's focus on the gas properties. So gas properties, no constant volume or shape, very low densities, very compressible, and they have high kinetic energies. Gas volumes are affected by three different factors: pressure, temperature, and change in the amount of gas. Because of this, we have to always calculate what the gas volume will be if any of these conditions change. Well, the first thing we want to do is check out air pressure. Now, air pressure is the weight of the air directly above you to outer space, that is. It's greatest at sea level because there's simply more air above you going to outer space. As you go up in elevation, the air pressure becomes less and less. So therefore, air pressure increases as you go down towards the surface. So in this country, our lowest air pressures are in cities like Denver or Santa Fe, where they're very high in altitude, whereas our highest air pressures are in places like deserts. In fact, I think our highest air pressure normally is in Death Valley in California. Now, air pressure is measured by a barometer, so let's check out a simple barometer. So here we have a dish with mercury in it, and there's an inverted tube that had mercury in it as well. You notice that most of the mercury is staying up in the tube. And what's keeping the mercury in the tube is the air pressure. Now the air pressure is pushing down on the surface of the mercury. You can see the arrows there, trying to keep the mercury in the tube. Gravity, on the other hand, is trying to pull the mercury out of the tube. Now this gives rise to our first pressure unit, which would be a distance unit. So at sea level, the air pressure is great enough to maintain a column of mercury 76 centimeters high. Now if you took this barometer up to a higher elevation, you would notice that the mercury would start to come out of the tube. And if you brought that barometer off the mountain, the mercury would go back up into the tube. So this gave people a way to measure our air pressure, which was very helpful, especially for ships at sea when storms would come up. Because as we know, with storms we have low pressure areas. In nice weather it's high pressure. So with a ship at sea then, a storm could come up very rapidly and they have no place to hide from it. And so to know that the storm is coming would be most beneficial to them. Now the units of pressure that we're going to check out now, it's about 5 or 6 of them. And these are all what we call standard pressure, and they're all equal to each other. So the first one we have is an atmosphere. That's our largest pressure unit. So 1 atmosphere is equal to 760 millimeters of mercury. That's also equal to 760 torr. Now, the Italian scientist that invented the barometer was called Torricelli, and that's where we get torrs from. In the metric system, we use kilopascals, and so standard pressure would be 101.325 kPa. In this country, we have a psi, a pounds per square inch, and standard pressure is 14.7 psi. Now we want to take a moment to do a couple of conversions because you're going to have to do this in some of the problems. So I'm going to take a look at 2 of them. And the question is, convert 1.10 atms to millimeters of mercury, and then also convert it to kPa. All we have to do is know the 2 conversions, and here they are. So why don't we stop for a second, and you can pause this, and you do the conversions, then we can go back and check out your answers. Okay, let's check out the answers now. So for the first one, you see, we'd have 836 millimeters of mercury, and the second one would be 111 kPa. Next thing we want to check out is, what about a container that has a gas in it? Does it create pressure the same way that the air does? And the answer is no. So we're taking a look on the left here at a piston cylinder setup. We have the gas trapped inside the cylinder. Now the pressure in that cylinder is created by the gas molecules causing collisions between themselves and the walls of the container. So here the key word is collisions. Anything that would increase the number of collisions or the force of those collisions will increase the pressure. So how do we measure the pressure of the gas that's confined like that? We don't use a barometer. Instead, we use manometers. And here are two simple manometers. Now you might have noticed one on the left there. You see these kind of valves on large tanks of gas. And here on the one on the right, we have a blood pressure cup, which is also called a sphygmomanometer. And so the blood pressure cup works by pumping air into the cup enough so that it cuts off the blood flow. And then the person listens for the blood flow to resume as they let the air out of the sphygmomanometer. We also have two kinds of manometers that we could see in a lab. One is called the closed-end manometer, and the other is an open-end manometer. So let's start with the closed-end one. So we start off with the gas in the container. We see that yellow gas. Now that gas is causing pressure and is trying to push the mercury away from itself. See how we have the black arrow showing you that. So the pressure is going in that direction. And because it can't get through the stopcock, it's pushing on the mercury. Now the pressure of that gas would simply be the height of the level of mercury. It's the difference in those two levels. So you see how the H is represented here. So the pressure of the gas is simply the height of it in the tube. Now the difference between the closed end and the open end is that with the open end, we have the air pressure to contend with. Now the gas is still creating pressure in that direction, but now the air is also creating pressure in the opposite direction. So the pressure of the gas in this case is going to be the sum of the height difference and the atmospheric pressure. You're probably going to see a couple of questions like this in the Connect assignment, and I'm sure there's going to be one on the exam as well. All right, now let's take a look at that same condition that we had a moment ago with the piston cylinder apparatus. So next question is, what would happen when the pressure on the piston is doubled? What do you predict would happen? Well, let's check it out. If we were to double the pressure, let's say it went from 100 kPa to 200 kPa, the volume would be cut dramatically. Now you notice that the new pressure is gone up from 100 to 200 as well, and that's because the particles now are much closer together, and so the number of collisions between the particles and the walls of the container, the number of collisions has increased dramatically. In fact, they probably doubled. So what we notice then is the volume went from 1 liter to a half a liter when we doubled the pressure. It's kind of like an inverse relationship. In fact, that's exactly what we have. Now, if I take my pressure and volume from my first condition and multiply them together, I get that. It's going to call those ones P1 and V1. And if I do the same for my second conditions, you notice I get the same answer. I'm going to call those P2 and V2. And since they both gave me that same number, I can then say that these two equal each other. And this is our first gas law. P1 V1 equals P2 V2. And this is called Boyles' law. So that's our first gas law. We're going to have a few others. Now, next situation we're starting off with, we have two beakers, a large beaker that has some water in it and a balloon. And sitting on top of that balloon is a smaller beaker that has water in it as well, so it's putting weight on the balloon. And that large beaker is sitting in some ice. And we're starting off with the volume of the balloon being 150 milliliters and the temperature being 273 Kelvin or 0 centigrade. So we're going to find that when we deal with gases, we have to have our temperature in Kelvin degrees. So what will happen to the volume of the balloon if the beaker is heated to 373 degrees or 100 degrees centigrade? Well, let's see. Wow, notice how large the balloon has become now, so much so it's pushing that beaker with water in it right out. So let's see, what would our new volume become? Could you have predicted what it would become? Well, it would become 205 mLs. And this gives us Charles' law, which is V1 over T1 equals V2 over T2. So what we say here is volume and temperature are directly proportional to each other, but you must have the temperatures in Kelvin degrees for this gas law to work. So you must remember that. And you can see by just plugging in the data, we would cross multiply and solve a V2, and we would come up with 205 mLs.